Hello guys, Dr. Hasbullah here, and in this video we're going to be looking at compressible flow. A compressible flow is a flow in which the density changes a lot along the streamline. For example, in a pipe, right, when the flow moves from point A to point B inside a pipe, if the density change between A and B, then we can call it a compressible flow. Usually, compressible flow applies to gases, alright? It doesn't apply to liquid because liquid is very difficult to compress, right? But if the gas is moving at low velocity, then quite often the density doesn't change. So we still call the flow incompressible even though it is a gas. But if the velocity is high, it's likely that the density will change. And in that instance, we're going to call the flow compressible flow. To analyze compressible flow, you're going to need to get familiar with a few concepts that I suspect that you already know, but maybe you forgot about it, so let's refresh that. First of all, to study compressible flow, we usually need to use the ideal gas relationship. And that relationship is P equal to rho RT, right? So P here is pressure, rho is density, R is the gas constant, that is 287 kilojoule per kilogram dot Kelvin, right? And temperature, T is temperature. Alright, and when we use this equation, you need to make sure that the temperature is in Kelvin. Right, and also very often we're going to assume that the flow, when we study compressible flow, we're going to assume that the flow is isentropic and also adiabatic. So isentropic means that there are no change in entropy. The delta S is 0. Right, and also adiabatic means that the delta Q is 0, meaning that there is no heat transfer to and from the flow itself. So delta S is governed by this equation, which is Cp ln T2 over T1 minus R ln P2 over P1. And I think you have covered this in thermodynamics, right? So I'm just going to carry on, right? And we agreed that delta S is equal to 0, right? So now let's see what happens to this equation. So we're going to end up with Cp ln T2 over T1 equal to R ln P2 over P1. And when we are dealing with ln, we can always bring Cp and R to here. So T2 over T1, this is ln to the power of Cp equal to ln P2 over P1 to the power of R. Right? And if we just remove the ln from both sides, so you'll end up with T2 over T1 to the power of Cp equal to P2 over P1 to the power of R. Right? But we know that R is actually equal to Cp minus Cv. And also, Cp over Cv is called the specific heat ratio, which is K. Right, and if I can manipulate this equation, right, I'm going to write here T2 over T1. This is equal to P2 over P1 R over Cp. Okay, and we know that R equal to Cp minus Cv. So let's do this R. Let's solve for this term. Right, so R over Cp equal to Cp minus Cv divided by Cp. So this is 1 minus Cv over Cp. Okay, and this is equal to 1 minus 1 over, or we can write this as K minus 1 over K. Right, so there you go. The relationship between T2 and T1 is actually P2 over P1, K minus 1 over K. Right, and if I go back to my ideal gas equation, which is this one, right, and I know that P equal to rho times R times T, so T must equal to P divided by rho times R. Okay, so T2 over T1 will be P2 over rho 2 R divided by P1 rho 1 R. Okay, so here is equal to P2 over P1 rho 1 over rho 2. I can cancel R out. Okay, so if I replace it here, T2, if I replace here to here, I'm going to end up with P2 over P1 rho 1 over rho 2 equal to P2 over P1 K minus 1 over K, right? So I can also do this, rho 1 over rho 2 equal to P2 minus P1 to the power of K minus 1 over K minus 1, right? So what happens now is I'll end up with P2 over P1 to the power of minus 1 over K, right? And if I shift this, I'm going to get rho 2 over rho 1 equal to P2 over P1 to the power of 1 over K, right? I hope that makes sense to you. And if I do P2 over P1, this is going to be equal to rho 2 minus rho 1 to the power of K, right? And if I rearrange it a little bit, right, I'm going to get P2 over rho 2 to the power of K equal to P1 over rho 1 to the power of K. And because of this relationship, I can also say that P divided by rho to the power of K equal to a constant. And remember, you can only get this relationship, right, by assuming that the flow is isentropic and adiabatic, right? If the flow is not isentropic and is not adiabatic, then you cannot use this relationship. But don't worry, I think for most of the problem involving compressible flow, we're always going to assume isentropic and adiabatic. Okay, and right now I want to introduce to you to a concept that is called speed of sound. Okay. Speed of sound. And what is the speed of sound? It is exactly what it says, which is the speed of sound. And you need to understand that sound is actually a little disturbance in pressure. So for example, when I speak, right, a diaphragm in my throat is actually creating a pressure disturbance in air, right? And this pressure is moving through air at a certain speed until it reaches your ear. Okay, and this little pressure disturbance, the speed of that pressure is called the speed of sound. And the symbol for the speed of sound is C. And speed of sound changes according to temperature. Okay, and I'm going to prove it to you. We're going to derive the equation of the speed of sound. If you imagine a pipe, right? A pipe, and the flow is not moving inside this pipe. Okay, the flow is not moving, but there is a little pressure disturbance that moves from left to right. Okay, and this pressure looks like this. Okay, maybe I'm going to give this different color. Let's do blue. Okay, so the pressure is moving to the right, and at what speed? Of course, at the speed of C, which is the speed of sound, right? And when the pressure is moving from left to right, and remember I told you before that inside this pipe, right, the velocity is 0. The velocity of the flow in pipe is 0. It's just that the pressure is moving. When the pressure is moving, it doesn't mean that the gas is moving as well. For example, if I speak to you, you can hear my voice, right? But you don't feel like a wind or something, right? So the air isn't moving. What's moving is the pressure. Okay, so that's why the velocity here is 0, right? And let's say to the right side of this pipe, I have here my pressure, my density, and also my temperature. But on the left-hand side of the pressure wave, there is a change in pressure, density, and temperature. Okay, and I'm going to call this P plus delta P rho plus delta rho, and temperature plus delta temperature. Okay, and also when the pressure wave has gone through the pipe, okay, it will actually excite some of the particles so that it also moves at velocity of delta V. Right, there is some little movement behind. And now let's analyze this in terms of control volume so that we can derive the equation for C. Okay, and to do the control volume analysis, I'm going to draw another pipe. Okay, but now instead of the pressure moves from left to right, okay, I'm going to assume that the pressure stays constant, but we as the observer is actually moving through the pressure. Okay, so let's see what's happening, right? So let's say now we have here the same wave, but we freeze it in time. Okay, so here, because when I do this, the velocity on the right hand side of the wave now is no longer 0, right? It has to be c in that direction. Okay, and velocity on the left of the wave is going to be c plus delta v, right? And the rest is the same. Okay, so this is still p, rho, and temperature. This is still p plus delta p, rho plus delta rho, and temperature plus delta temperature. Okay, this is not very difficult to imagine, right? Imagine if you are driving a car at 80 km per second, right? You are sitting in a car, you are moving through air, right? The air is not moving, but the car is moving, right? So the car is moving, right? If you want to analyze the car, it is similar if you assume that the car is constant. Sorry, it is similar if you assume that the car is not moving, but the air is moving at 80 km an hour. Right, so it's the same frame of reference, right? And now I'm going to take a little portion here to do the contour volume analysis, right? And I'm going to bring it here. Okay, and this is the wave again. Okay, and what is going into this control volume is, okay, we know that m dot is rho times velocity times area. Okay, so on the right hand side, we have rho times velocity. What is our velocity now? Remember, our velocity is c, and our area is the area of the pipe. Okay, so A. So that is the mass flow of the fluid that goes into the control volume. How about the mass flow of the fluid that goes out of the control volume? Okay, so on the left hand side of the wave, right, rho has changed, velocity has changed, but area is still the same, right? It's the area of the pipe. Okay, so this is actually rho plus delta rho times velocity is now velocity of the fluid plus c. Okay, so this is now c plus delta v times A. Okay, so that is the mass flow in, and this is the, so this is the mass flow in, and this is the mass flow out, right? So we know that in steady flow, whatever goes in must comes out. Okay, so mass flow in is actually equal to mass flow out. Now let's write the equation. So rho times c times area equal to rho plus delta rho c plus delta v times A. Okay, and let's try and solve this. So this is rho times c times A plus rho times delta v times A plus delta rho times c times A plus delta rho delta v times A equal to rho times c times A, right? And immediately there are a few things that you can cancel out. Okay, so rho CA and rho CA is going to cancel out each other, and then delta rho delta V here. Okay, so delta is the small change, right? So when you have two deltas together, it is safe to just neglect it, right? Because it's going to be too small to calculate. So I'm going to cancel this out as well, and we end up with something quite simple, which is rho times delta V equal to minus delta rho times C times A. Okay, sorry, this is A. right? And you can cancel A out. So this is rho delta V equal to minus rho times C. Okay, and this is the equation that we get from continuity equation from our control volume analysis. Alright, now what happens if we consider the force into and exit of the control volume? And this is when we do the momentum analysis using momentum equation. And what does the momentum equation tells you? So momentum equation is F equal to MA, and this is equal to M dot V2 minus V1, right? And what are the forces inside this control volume? Okay, and the forces inside this control volume goes in, and forces, remember, the pressure force always goes in. Okay, so force is equal to pressure times area, right? So for this term, it is simply pressure times area. But for term on the left, this is pressure plus delta P times area. Okay, remember the pressure has changed from before to after the wave. At the right hand side of the wave, pressure is P here, but at the left hand side of the wave, the pressure is P plus delta P. P plus delta P. Okay, and this is what I write here. Okay, and that is our force. So force is P times A minus P plus delta P times A equal to M dot. What is our M dot? We know that M dot in equal to M dot out. So M dot in is this, and M dot out is this. So I rather choose the simpler one, which is rho times C times A. Okay, and we do V2 minus V1. So V2 is on your left hand side. Okay, so velocity on the left of the wave is now C plus here, right? Okay, so C plus delta V minus V1 is the V to the right hand side of the wave, that is here. Okay, just C minus C. Now let's work on this equation. So it's quite obvious here. You're going to cancel PA with P and A. So you're going to end up here. So you're going to end up with minus delta P times A. And this is equal to C here. Cancel with this one. So this is rho times C times A times delta V. Right? And I'm going to remove this A. Okay, so minus delta P is equal to rho times C times delta V. And here is our second equation. Okay, so this is our equation number 1. And this is our equation number 2. Okay, and we're going to use these two equations to find the solution. And I'm going to use delta V as the title, right? So delta V is minus delta P over rho C. Okay, and this here, I'm going to put it into here. Okay, and before that, I think we missed something here. This is going to be minus delta rho times C. Okay, so rho delta V equal to minus delta rho times C, and we know what delta V is. Alright, so this is rho times minus delta P divided by rho C equal to minus delta rho C. Okay, quite straightforward. So rho divided by rho, you can cancel that out. And then C going up, going to be C square equal to, and minus sign over minus becomes positive. So this is delta P over delta rho. Okay, and C now is equal to square root of delta P over delta rho. Okay, so now it's quite obvious that the speed of sound depends on the square root of the change of P divided by the change of density. When you find this term, then you can find what is your C. Okay, now let's carry on. Okay, so delta P over delta rho, because the change is quite small, right? You can also write this as dP over d rho. Okay, so now basically you need the relationship between P and rho, right? The pressure and density. Now, if you remember, just now when we did the isentropic relationship, you have got something to relate pressure and density, right? And that relationship is actually this one. Okay, this is the relationship that we are looking for. Alright, so P over rho to the power of K is constant. Okay, so P over rho to the power of K is constant. Okay, and can I do here constant equal to, let's say our constant is B, right? And I'm going to do P equal to B times rho to the power of K. So dP over d rho is actually K times B times rho to the power of K minus 1. And if I were to rearrange this, right, I can write this as K times B times rho to the power of K divided by rho. And rho to the power of K, I can manipulate this in such a way that rho to the power of K is equal to P divided by B, isn't it? Right? So this is actually K equal to, so this is actually K times B times P over B divided by rho. And you end up with K P over rho. And this is your dP over d rho. Right? And if I put this equation back again into this C, right? So you're getting close now. Okay? So now this is a square root of K times P over rho. Let's go back to our ideal gas equation, which is this one. Okay? And you'll end up with P equal to rho times R times T. So P divided by rho equal to RT. Okay, and your C now, okay, let's bring this down. So C is square root of K RT. Right? So that's it, guys. This is the expression for C, the simplest form of expression that we can find for C. Let's figure out about this equation. So K is specific heat ratio. And for air, K is usually equal to 1.4, right? And R, as usual, is gas constant. Okay, and the value is, normally is 287 joule per kilogram dot Kelvin. Okay. Okay, so because this is 287, sometimes we use 0.287, right? But 0.287 if the unit is in kilojoule, right? And if you use joule, it is 287. So I may have made a mistake here at the very beginning. Okay, so here is incorrect. And I'm going to remove this and replace this with joule. Okay. So just a recap, what is a gas constant? So gas constant is the amount of energy that you need to raise the temperature of anything by 1 degree Celsius or 1 degree Kelvin for 1 kilogram of the medium. Okay, that is the amount of the energy that you need. Okay, and temperature, I think I told you before that this is temperature and you must use Kelvin as the unit, right? If you use Celsius, you might get it wrong. Okay, now how do we use this equation? It's quite simple. Okay, let's say I'm recording this at night. So let's say the temperature outside, the ambient temperature is 25 degrees Celsius. Okay, so 25 degrees Celsius, my temperature is 25 degrees Celsius. So just from this temperature, I can actually find what is the speed of sound. So if I'm speaking to you now, if you are in the room with me, then the velocity of the sound that's going to reach you, I can calculate it exactly at this temperature. Okay, so C is equal to square root of K RT. So now K is 1.4, R is 287, T is 25 plus 273. Okay, and I'm going to end up with 1.4 times 287 times 25 plus 273. Square root of that, this is 346 meter per second. Okay, now that's quite fast, right? 346 meter per second. If you convert it to kilometer per hour, right? We are familiar with kilometer an hour, right? So that's about 1,000 kilometer an hour. Okay, so that is the speed of sound. And if you notice, if you increase the temperature, then the speed of sound will increase as well. Okay, right, now that you know the speed of sound, okay, there is another term that you should understand and you should know very well, which is called the Mach number. Okay, now if I could walk very fast or I could run very fast, and I could run as fast as my voice travels, okay, then my Mach number will become 1. Okay, so Mach number is actually the velocity of the fluid, or the velocity of the body, or the velocity of the jet, right? Divide by the speed of sound. Okay, divide by the speed of sound. If I have Mach number less than 1, right, then the flow is called subsonic. Subsonic. Let's say you are moving along the highway, Mach number, and your velocity is 100 km an hour. Okay, and the speed of sound is 1,000 km an hour, right? So your car is moving at 0.1 Mach number. Okay, your car is moving at 0.1 Mach number, right? And if Mach number is greater than 1, okay, this is called supersonic flow, right? And you can achieve this in a jet, in a fighter jet. Okay, in an airliner, right, usually the Mach number is around 0.8. So the passenger aircraft is moving at subsonic speed, okay, and the jet fighter is usually moving at supersonic speed. So if the velocity of the jet fighter is, I don't know, maybe 3,000 km an hour, right, and the speed of sound is just 1,000 km an hour, so the Mach number for the jet is actually 3. Okay, so the Mach number for the jet is 3. Okay, and if you imagine, right, this is quite exciting, right, when you talk about supersonic flow. Okay, when, let's say you are moving with a car, right, so at 0.1 Mach number, right, and you see a car coming towards you, right, you can hear the sound of that car coming, right, so you know there's a car coming, right, but for the supersonic jet, right, because the jet is moving faster than the speed of sound, right? If the jet is coming towards you, you never hear anything, right? Because the sound is actually behind the jet. Okay, if it's moving at supersonic speed, you never hear it coming. Okay, so that's quite exciting, right? But if Mach number is high, that is greater than 5, you're gonna call this hypersonic flow. Hypersonic flow. Okay, so this is very rare. Okay, maybe high-end fighter jet has this, and this is called the hypersonic flow. Right, so that's it, guys. This is something that you need to remember. Okay, so Mach number is basically the velocity of the fluid, or the velocity of the body, divided by the speed of sound at that time, because the speed of sound might change with temperature. And I think this video is going for a bit too long, okay? But now you need to know that we have derived two things, okay? Which is C equal to square root of KRT, okay? That is the speed of sound. And also that the Mach number is velocity divided by speed of sound, right? So try and repeat the derivation. See if you can do it without even looking at this video, right? And then you can move on to the next video. Okay, so thank you guys. I'll talk to you soon. Bye.